Hello, my name is Chris Felix, and today I will be talking about cured resin-based composites in dentistry. A good place to start is looking at some of the potential common misnomers that exist in dentistry. By way of instruction, sometimes light curing is assumed that it's easy, and the only instruction provided is "and then you light cure," or curing through the tooth, or providing additional curing on the last increment, or to confirm hardness to just probe the top surface, or that LED curing lights do not generate significant heat, or that multiple peak LED lights can cure all materials, increments of composite can be cured in under 5 seconds, or just doubling the curing time to avoid undercuring. So those are just some potential common misnomers that certainly exist in dentistry. Also, we do have some potential questions and answers that generally only generate more questions, but from a researcher's standpoint, they are generally interested in what is the best material or composite, and certainly an answer to that would be a composite that is accurately cured. From a manufacturer's standpoint, they're generally interested in how much energy should be recommended. And the answer to that would be enough to deliver the manufacturer's intended physical and performance properties. Now, a dentist might ask, how long do I need to use the light? Do I follow the LCU instructions or the RBC instructions? And certainly the answer to that would be depending on the LCU and the RBC and the LCU operator's technique. Now, in this study we disaggregated transmittance, and the reason why we did this is that most materials contain different photoinitiators or photoinitiator combinations, and here we see 3 fairly common photoinitiators. The camphorquinone is a fairly yellow material and is activated by blue light with a full width half max of 430 to 489. TPO, a whiter compound with a full width half max of 358 to 405, basically activated by violet light. And PPD is kind of activated by violet light, but it goes all the way up to 440, which is into the blue range. Now, comparing the photosensitivity of these 2 photoinitiators, looking at the CQ and the TPO, we can see that the relative absorptivity of the TPO is much higher than the CQ, where the peak absorption is almost 5 times more than in the TPO in comparison to the CQ. But if we overlay some common spectra for single peak and a dual peak curing light, we see here that the blue components are overlaid very well in the peak absorption area of the camphorquinone. But what we see here is that in the violet area, where we see the violet LED chip in the dual peak curing light, it provides much less violet light in comparison to the blue light, and the relative absorption peak, or the peak of the absorption spectra, I should say, for the TPO, it's not matched up very well where the photons of violet light are coming from the dual peak curing light. And that's because it's very difficult to get wavelengths or photons around 380 through materials. So in this study we focused on the measurement of transmittance. So we're looking at light coming out of the light tip and impacting on the top surface of the material, and of course we do have reflection going on. But what we wanted to do was to disaggregate the light into 2 spectral ranges, 380 to 420 for the violet and 420 to 540 for the blue. So we need to understand a bit about physics to understand what's going on with curing dental materials, because we have refraction and reflection, we have absorption and diffusion, and of course then we have transmittance all going on. So from the light tip we have diffusion of light exiting the light tip, and depending on the distance it travels down to the surface of the material, where then we have some of the light is reflecting, and then the light that's entering into the sample, there is diffusion and there is absorption from the photoinitiators, but there's also absorption from the other components like the monomers and fillers. Now, the resin composite chemistry, we have the photons interacting with the photoinitiators, and they're generating free radicals, getting the polymerization process going. And we can look at 3 potential saturation cases. One where there's no remaining photoinitiator. If there's no movement in the material, if the material is all locked in place, even if the photoinitiators are generating free radicals, the monomers or polymer chain ends may not be able to move anymore. Or we can have the case where the photons that are available are not matched up with the photoinitiators that are available. And we can then see that the free radicals are not generated. But in the end, transmission is the most important measurement, because out of all of the energy that is delivered and all of the other interactions, what actually makes it to the bottom surface, what type of light, and how much to make sure that the bottom surface is sufficiently cured so that it can be bonded well to the increment or bonding agent below it. The methods we use in our studies, we took a single peak curing light and a dual peak curing light, and we calibrated each of them to deliver 1000 milliwatts per centimeter squared to the top surface of the samples using the Mark resin calibrator. We looked at 4 shades of resin-based composites. We looked at the Tetric Evo Ceram shades A2, D3, the Bleach I, and the Bleach XL. And then we did 1, 2, and 3 millimeter increment thicknesses. The RBCs were cured repeatedly in 10-second curing cycles until saturation was achieved. And then we measured the transmission using the Mark resin calibrator. So to confirm saturation, we repeatedly cured the samples. As you can see in the real-time transmission graph, the transmission is changing as the material is polymerizing. And generally it's because of two different effects. One is that the photoinitiators are absorbing photons to generate free radicals for the reaction, which is a very small effect on the transmission. But most RBCs have a change in index of refraction as it goes from the uncured to the cured state, and that's quite a large effect. So we can see here, once the transmission has stabilized, and in this case after 3 curing cycles, then we know that the material is no longer changing and the polymerization process has been completed. So in disaggregating the energy from the 2 LCUs, we deliver 10 joules over 10 seconds. And the single peak curing light, of course, most of its energy is in the 420 to 540 range. The dual peak curing light had 1.6 joules in the violet range and 8.4 joules in the blue range. Looking at our first results graph, we can see here for the bleach I, which is a fairly translucent shade, we're looking at the results for the dual peak curing light, so the blue light range versus the violet light range. And we can see at 1 millimeter thick that almost 42% of the light is getting through, where in comparison only maybe 18 or 19% of the violet light is getting through that 1 millimeter increment. And as the increments increase, we certainly see that ratio of violet to blue light increase as well. So there is, maybe 5% of the violet light getting through in that third 3 millimeter increment, where still 25% of the blue light is getting through. And this trend follows along with the other shades, although they're a little bit more opaque. The D3 and the A2 were very similar, but the Bleach XL was quite opaque. Looking at the spectral transmission from some of the tests, is that we can see here the single peak curing light, what was delivered to the top surface, only 14% transmitted through to the bottom surface in the blue range for the shade A2 at 2 millimeters thick. Comparing that to the dual peak curing light, in the blue range, almost 17% transmitted through in the blue range, and only 3.5% transmitted through in the violet range. So we can see here there is a difference between the blue range of the two curing lights. And we can attribute this to the difference in curing light optics. Here we have a performance over distance of both curing lights. And we can certainly see here that the dual peak curing light has optics that maintains its intensity over distance, where the single peak seems to drop fairly quickly. And looking at the beam profiles, we can see here with a single peak, of course there's no light in the violet range, but we can see here that in the blue range that the distribution of intensity over the tip is fairly focused into the center, which doesn't lead to good performance over distance. But from the dual peak curing light, we can see that the violet component and the blue component, it has much different optics that help its performance over distance. We ran some stats to confirm that the single peak gave a lower percentage transmission of blue light than the dual peak LCU, although they were fairly close. The percentage transmission of blue was significantly higher than violet light for the dual peak. The proportional difference between the blue and violet light transmission was mainly affected by sample thickness, with shade being borderline significant. So the points to discuss would be that measuring the spectral transmission of light through RBCs during curing and after the saturation point provides really good insights into the polymerization process as a quick bulk property test method. Evidence that curing light optics have an effect on the percentage transmission through RBCs. Insights into the proportional ratio of violet to blue light when identifying energy requirements. Method for identifying saturation by measuring real-time transmission for a specific LCU and RBC combination. Transmission measurements are critically important because the correct amount type of light energy needs to reach the bottom surface to ensure safe levels of biocompatibility. So the study conclusions would be that the higher peak in the TPO's absorption spectrum relative to CQ may be offset by the spectral range of the violet light being where the spectral absorbance of TPO is lower. So there's a mismatch of where the photons of violet light are coming from the LCU to where the TPO absorption spectrum is most efficient. And certainly the LCU output in the violet range is much lower than in the blue range. Violet light has a lower percentage transmission than blue light, and transmission measurements are the essential starting point to all other properties testing done on RBCs. So we certainly need some more answers to make sure that we can facilitate the communication and application of research findings. And researchers can identify the minimum energy requirements by studying the saturation point of LCU and RBC combinations and provide the information to manufacturers. Manufacturers can provide better instructions for clinical use of LCU and RBC combinations to the dentist. And dentists trust reputable manufacturers and can stay away from using poorly engineered LCUs and from the latest unfounded marketing claims to minimize potential problems of post-op sensitivity and restoration failure. And that's it. Thank you for listening.